This video is about the dynamic characteristics of operational amplifiers. So the gain of an operational amplifier is not the same at all frequencies. The open loop gain is the gain without feedback. The open loop gain is constant at low frequencies, but then starts to decrease at higher frequencies. Here is a voltage follower with a 1 kilohertz input. And we can zoom in and see. So we see here that the input is between 4 volts and 6 volts, and indeed the output is between 4 volts and 6 volts. The input and the output are in phase. Everything's fine. Here we have with a 50 kilohertz input, and the output still matches pretty closely. We can zoom in and see. So again, we see it's pretty much going from 4 volts to 6 volts, and it's still in phase. Here it is on the same scale. Again, so we can see it's pretty much from 4 volts to 6 volts. But now by 100 kilohertz, the output is starting to diverge from the input. You can already see that now we have more of a triangle wave than a sine wave, but let's zoom in a little more. So here we see that it's still going to about 6 volts and down, but it's not getting down to 4 volts. It's getting down to about 4.2 volts. And we'll notice that there's a little bit of a phase offset too, that we're not quite in phase. So here we are where we've made the same scales. So again, we can see that we're not quite getting down as far. The signal is a little bit smaller. Now, with a 500 kilohertz input, then the change is much more clear. So let's look in. So now we can see that again, when the input signal goes from 4 to 6 volts, the output signal is much reduced. It's only from about 4.9 volts to about 5.3 volts, and we notice now we can clearly see a phase shift of about 90 degrees or so from the input to the output. Here it is on the same scale, and on the same scale, even without zooming in, we can see how clearly the amplitude is smaller and the phase is offset. So the roll-off can be seen in this figure. So we show the gain on a logarithmic scale vertically and the frequency on a logarithmic scale horizontally. So the open loop gain is flat for a certain range, and then it starts to drop off as the frequency increases. The closed loop gain, meaning the gain with feedback, is flat up until it runs into this curve. As soon as it runs into the curve of the open loop gain, then it has to follow it. The rate of this roll-off is 20 decibels per decade. The frequency at which the gain is 1 is called the unity gain frequency. So a Bode plot is logarithmic in both frequency and gain, as the graph that I just showed you. The straight line indicates the gain is inversely proportional to frequency, so the gain is proportional to 1 over f. The gain is often expressed in decibels rather than simply as a ratio of output to input. And the gain in decibels is 20 times the log of V out over V in. A change by a factor of 10 in V out over V in is a change of 20 decibels. A decade is a factor of 10, so a roll-off of 20 decibels per decade represents a decrease in the ratio of V out to V in of a factor of 10 as the frequency increases by a factor of 10. The inverse relationship between frequency and gain can be expressed various ways. So the gain bandwidth product is the gain times the frequency, and the unity gain frequency is the frequency at which V out over V in equals 1. I will use the term A to refer to that ratio and G to refer to the gain in decibels, so that whenever I use the symbol G, it means decibels. When I use A, it just means the ratio of the output to the input. This convention is common but not universal, so when you see stuff about the gain, make sure that you understand which way it's being expressed. So, as I said before, when negative feedback in an op-amp circuit is employed, then the closed-loop gain is decreased. As the frequency increases and the open-loop gain decreases due to roll-off, the values of the open-loop and closed-loop gain eventually coincide. From this point on, the closed-loop gain also begins to experience roll-off at the same rate. So the closed-loop gain can never be greater than the open-loop gain. Thus, the unity gain frequency for an op-amp circuit is the same regardless of the mid-band gain. So, another factor in op-amps is called the slew rate. When the inputs to an op-amp change, it takes time for the output to change. So, in this case with a square wave input, the output will take a finite amount of time to reach the output voltage and then a finite amount of time to fall again. So the rate of possible change of the output voltage is referred to as the slew rate. So here's the output of voltage follower at 100 kilohertz for a sine wave input. So you'll see that we see this sawtooth, because basically this sawtooth represents the slew rate of the amplifier. So the rise or fall of about 1.6 volts happens in about 5 microseconds, so this gives a slew rate of about 0.3 volts per microsecond. The slew rate is defined as the maximum rate of change of voltage output, and it's usually given in volts per microsecond. Now, there is an interaction between the amplitude and the slew rate. So the slew rate equals the maximum rate of change of the voltage. So if we have a sinusoidal signal, so A sine omega t, then if we take the derivative is WA omega A cos omega t. So the maximum of that, since the maximum of the cos is 1, is just going to be omega A, and omega is the angular frequency, which is 2 pi times the frequency. So the maximum rate of change of the voltage is 2 pi times the frequency times the amplitude. So that maximum rate of change is the slew rate. So for a sine wave, the slew rate is 2 pi f times A. So if we rearrange this, we see that the maximum frequency is the slew rate over 2 pi times the amplitude. So the higher the amplitude, the lower the maximum frequency you can have without distortion. And sine waves will be the least distorted of any waveform. So here's the previous circuit. 1 volt, 500 kilohertz into a voltage follower. So again, let's zoom in so you can see. And clearly, you can see that the amplitude is reduced and the phase is shifted. So here we go. Now, reducing the input to 0.1 volts makes the output much closer. So you see now, our input voltage is between 4.9 and 5.1 volts, and our output gets very close to 5.1, very close to 4.9, and the phase is almost the same as the input. One of the uses of op-amps is to produce circuits which are used to amplify or attenuate a certain range of frequencies. These are called active filters. So a low-pass filter allows frequencies below a certain corner frequency to pass and attenuates those above. Note that the corner frequency isn't really an absolute limit. It's the point at which attenuation begins. So it's actually defined as the 3 dB point at which the gain differs from the mid-band gain by 3 dB. So if you're expressing gain without using decibels, it's the point at which the gain is the mid-band gain divided by the square root of 2, so about 70% of the mid-band gain. So a low-pass filter and its Bode plot are shown in the following figures. So there's all kinds of designs for filters. There's whole courses on it. The ones that I'm showing here are just ones that are simple to analyze. So here is an inverting amplifier with a capacitor in parallel. So at low frequencies, this capacitor will basically look like an open circuit. So at low frequencies, this will just look like an inverting amplifier. At high frequencies, this will look like a wire, and so this resistance will basically be shorted out. So this is what the Bode plot looks like. The pass band is up to here. This is the corner frequency, and so on. So as I said, in the feedback part of the circuit, At low frequencies, the capacitive reactance is about infinite, and so the gain is that of a normal inverting amplifier. At the corner frequency, the capacitive reactance equals the feedback resistor. Above this frequency, the impedance is inversely proportional to frequency. A high-pass filter allows frequencies above a certain corner frequency to pass and attenuates those below. And again, just like for the low-pass filter, the corner frequency is not an absolute limit. It's the point at which amplification begins. The high-pass filter, though, has a limitation due to the roll-off of the op-amp itself. As with any amplifier circuit, it's never possible to have gain above the open-loop gain of the op-amp, so any high-pass filter is actually a band-pass filter, which will be discussed below. So a high-pass filter and its Bode plot are shown in the following figures. So now we've just added a capacitor in series with the input resistor of an inverting amplifier. So at low frequencies, the capacitor is essentially an open circuit, so no signal goes in. At high frequencies, the capacitor essentially becomes like a wire, so at high frequencies, this becomes a normal inverting amplifier. So at low frequencies, nothing goes in. Above the corner frequency, we have an inverting amplifier until we reach the roll-off, the open-loop gain roll-off, in which case, that's what we have. A band-pass filter combines a low-pass and a high-pass filter to allow frequencies between two corner frequencies to pass and attenuates those outside that range. So the next figure shows the Bode plot for a band-pass filter. So there we have a lower corner frequency, an upper corner frequency, and the pass band.